Good morning. My name is Adam Post. Michael Nelson and I will be discussing INDOT bridge preservation activities. I'm planning to go through some of the bridge preservation and preventive maintenance treatments we do at INDOT, provide some programming and maintenance statistics, and review some sample bridge and deck life cycle scenarios. I'll then turn it over to Michael, who has some revolutionary information on bridge deck curing. To achieve our condition targets for bridges, INDOT established a statewide 20-year plan, which provides a long-range plan of our bridge and large culvert assets. We use this 20-year plan to help come up with our short-range 5-year capital program. In addition to the capital program, we have a 5-year scheduled maintenance plan in place, which we use to perform in-house and contracted maintenance on thousands of structures each year. INDOT's bridge preservation program consists of rehabilitation and preventive maintenance projects. The rehabilitation projects consist of the major work types such as deck and superstructure replacement, substructure rehab, and bridge widening, which serve to restore the structural integrity or correct safety defects. These rehabilitation projects are typically done throughout the 5-year capital program by outside contractors. Preventive maintenance projects are performed to prevent, delay, or mitigate deterioration, and these are a mixture of condition-driven and scheduled projects. The condition-driven projects can be done by INDOT maintenance or outside forces, and the scheduled projects are usually done by both, although they typically are performed by in-house maintenance. To achieve our condition targets for bridges, INDOT established a statewide 20-year plan, which provides a long-range plan of our bridge and large culvert assets. We use this 20-year plan to help come up with our short-range 5-year capital program. In addition to the capital program, we have a 5-year scheduled maintenance plan in place, which we use to perform in-house and contracted maintenance on thousands of structures each year. INDOT's bridge preservation program consists of rehabilitation and preventive maintenance projects. The rehabilitation projects consist of the major work types such as deck and superstructure replacement, substructure rehab, and bridge widening, which serve to restore the structural integrity or correct safety defects. These rehabilitation projects are typically done throughout the 5-year capital program by outside contractors. Preventive maintenance projects are performed to prevent, delay, or mitigate deterioration, and these are a mixture of condition-driven and scheduled projects. The condition-driven projects can be done by INDOT maintenance or outside forces, and the scheduled projects are usually done by both, although they typically are performed by in-house maintenance. This slide shows some of the many condition-driven preventive maintenance activities. It includes such treatments as bridge deck patching and crack sealing, joint repair, and polymeric and rigid deck overlays. It also includes various superstructure and substructure rehab repairs, channel work, and other miscellaneous treatments such as slope wall, railing, and approach slab repair or replacement. These maintenance treatments are also referenced in Chapter 412 of the Bridge Design Manual. We also have our scheduled or cyclical maintenance treatments. This includes treatments such as bridge deck, drain, joint, and superstructure cleaning, bridge deck sealing, and brush control. We typically perform bridge cleaning and flushing annually and tree and brush removal about every 2 to 3 years as needed. Our deck sealing program is currently performed at around year 5 after a new concrete deck is placed, and we don't perform these again after a thin or rigid overlay is placed. However, we've used to have a concrete provision during construction which says that in lieu of sealing bridge decks, that pozzolans were allowed to be put in decks. Many contractors were adding these pozzolans to forego the time-consuming and time-dependent epoxy penetrating sealer. INDOT also saw the benefit to using pozzolans instead of the initial sealers, which tend to wear away quickly, so they recently updated the specs to require the addition of the pozzolans. And since this change, we're now looking at trying to get the initial silane sealer put on the decks around year 1 or 2, and again 5 years later in years 6 or 7 prior to installing a polymeric overlay around year 11 or 12. INDOT maintains just shy of 5,800 bridges and 8,800 large culverts. This chart shows a summary of the various capital programming projects for these bridges and culverts currently in the program for years 2021 through 2025. Of the approximate 3,200 total projects in the 5-year program, around 43% are dealing with deck-related projects. This percentage increases to almost 60% if you remove the 859 small structure projects shown on the last line. So INDOT realizes the importance of protecting the underside of the bridge, and we devote a large percentage of projects towards sealing the decks and deck-related treatments to keep harmful salt away from infiltrating the deck and the components below. We also realize the importance of preventive maintenance projects such as those mentioned on the previous 2 slides. The blue numbers to the right show that roughly 1/3 of our capital budget is spent on these preventive maintenance projects. This does not include the projects performed by our district maintenance forces, which is summarized on the next slide. This chart shows a summary of our in-house INDOT bridge maintenance activities for the past 5 years. These activities are completed on various cycles and are not eligible for federal funds. Bridge deck sealing is normally performed in conjunction with the deck crack filling if crack filling is needed. We also have permanent and temporary deck patching, which is also performed as needed. And then, like I said before, we perform the cleaning and flushing items annually on most bridges, and we also have the brush cutting items, which are done every 2 to 3 years as needed. In all, our maintenance crews perform work on almost all of our bridges over a 5-year cycle, a large portion which receive attention every year. This flowchart diagrams a sample deck life cycle for one of our typical bridges. After the initial bridge construction, we install the deck sealer, and this silane sealer is applied 1 to 2 times before any overlay is placed. And it's not applied again after an overlay typically. For some bridges, the polymeric overlay is then placed. We just started using these around 10 to 12 years ago, but expect them to last 12 to 15 years or longer, and hope to be able to install up to 2 prior to needing a rigid overlay. Rigid overlays are typically on a 20 to 25 year cycle. Most bridges might see 1 to 2 of these, followed by a deck replacement or superstructure replacement, depending on the structure type and the deck condition. And we like this replacement to happen close to the bridge midlife, so we can get another deck life cycle similar to what's shown here prior to having to replace the structure. All right, this figure shows a complete life cycle of a typical bridge. The capital treatments are shown along the top. This particular sample shows 2 thin deck overlays followed by a rigid overlay prior to the deck replacement, which is preferred to be close to the midlife. Then the cycle is repeated prior to the bridge replacement, which in this case is at year 120. The bottom treatments show some of the maintenance items performed in their respective cycles. Most of these treatments are done using our in-house district crews who work to keep debris and moisture away from the bridges to prolong the life and maintain our safe crossings. Of course, not every bridge is created equal, and the sample life cycles that I just displayed are not the same for every structure. There are many variables that can shorten or prolong the treatments or change them altogether. The bridge type and bridge details are important, as well as the concrete and rebar material specifications. The design quality, plan quality, and construction quality all have an impact. Other variables are the overall traffic and the truck traffic amounts, maintenance and preservation frequency and quality, and of course, environmental considerations. Maintenance of traffic is another consideration. If work is being done on a highly traveled corridor, it might make sense to do a treatment a couple years early and lose a little service life in order not to use the same MOT set up 2 years later along the same stretch of road. Depending on the road category, INDOT is willing to move a bridge project up anywhere from 2 to 5 years early in order to do the work in the same corridor as another road project. However, moving a project out to a later year does not follow that same rule and is more dependent on the structure condition and if it can safely last the additional time. The main goal is to attempt to match up with the pavement timing and make it 10 to 15 years before we need to come back and do the next capital treatment. Added travel lanes and geometric considerations is a related variable where you might also need to replace a bridge or a component earlier than expected. To sum up the standard deck treatments that INDOT performs to achieve added life, the common ones we use is an appropriate balance between routine maintenance and use of polymeric and rigid overlays. However, INDOT is always testing out new materials and treatments to improve on using what we know works to try to increase the life of our bridges. We have used polyester polymer concrete or PPC overlays on a couple of bridges and are currently in the evaluation period on these. Our maintenance staff has a mobile trailer set up for performing epoxy injection on concrete decks, which contain rigid overlays that have debonding, where we hope to get an additional 5 to 10 years of service life before the next treatment is needed. We've also investigated the use of different deck rebar and concrete coverings during construction. In fact, we're using stainless steel deck rebar with an initial LMC overlay on the new decks in the North Split interchange in downtown Indianapolis, which will be constructed over the next few years. We've also made concrete material advancements, such as by requiring the pozzolans in the decks at construction, which I mentioned earlier. And we're currently testing some advanced deck curing methods with an E5 admixture. But Mr. Nelson is the expert on concrete, so I'm going to turn it over to him so he can discuss bridge deck curing in more detail.
INDOT's standard curing process for bridge decks has historically been a 7-day wet cure. And after the 7 days, the curing is removed and that's it. The curing stops. In 2018, we had a contractor who, there was a misunderstanding of the specification, and they actually applied curing compound behind the screed. They did a wonderful job of applying the curing compound. They got it on white as a sheet of paper, as we are accustomed to referring to now. And again, they did a good job. There was just a misunderstanding that was not allowed for INDOT standard specs. So when we learned that this had happened, I certainly had a bit of a panic moment, and we required the next day that the contractor go out and put the water curing in place for the 7 days as we would traditionally have done. This deck was unique in that it had 2 large closure pores over the piers, and those were done later. So what you see is that, on either side we had the curing compound with the wet cure over the top, placed 24 hours later, and the closure pore was done with the standard wet cure. So I went out and looked at this deck in 2019, and I was surprised by what I found. The picture here shows the transition line. So on the left side of the picture, you can see a close-up of the wet cured portion, and there was some paste loss at the surface, the fine aggregate, and it looked generally washed. And then contrast that with the right side, where the curing compound was applied first for 24 hours, and the surface was very tight, very uniform, and it looked good. and there was a stark contrast between how the two surfaces appeared. Um, Now, so this was my first aha moment that curing compound is certainly appears to be a benefit. And we know that curing in lab conditions is wonderful with water curing, but out in the real world, there are certainly challenges to pulling it off uniformly. And this was again my first moment of recognition that there's clearly something here. It's also noteworthy that other DOTs do deck curing in various ways. Some states actually do this on purpose. They put the curing compound on behind the screed with the water cure on top. So what I had discovered isn't exactly anything new. It is done by other states. And then some states actually just do the water curing for 7 days. And then once the water curing is removed, they then proceed to add curing compound. Neither of those are things INDOT has traditionally done. So based on the observations from 2018 that curing compound had benefit, we decided to try it on purpose in 2019. We partnered with Milestone and we poured 2 bridge decks on I-865, one eastbound, one westbound. We did the curing compound behind the screed. We applied the water cure the next day within 24 hours, white as a sheet of paper, as we're used to saying. And again, it all was positive. The contractor liked it. They perceived less risk to damaging the surface at the time of placement. There was, less pressure on them on pour day, and so it was easier logistically for them. From INDOT's perspective, certainly more timely protection behind the screed, and everything just seemed to be, more smoothly. So overall, we tried it. The cracking was minimal, and if any, and Milestone ultimately continued on with this process and built several more of these decks even into 2020. And again, the response has been favorable of this process, and we really haven't seen any negative side to that. And we're continue to see benefits from the curing compound. So in 2020, we decided to try something new yet again. I'd heard rumblings over the past 4 or 5 years about a new admixture that had been developed around the Indianapolis area called E5 internal curing. The thought was that if the admixture does half of what it's supposed to do, in my mind, perhaps if we use that in conjunction with the curing compound, maybe we don't even need the water curing. So I pitched that idea to one of the area engineers, Mike Koch, in Fort Wayne, and he was interested. Then we had a contractor who was interested in Dan McCoy at RL McCoy. So one thing led to another. We did some lab trials at my office and tried some things to learn a few things. And then we decided to go forward on a deck. So in June, we tried it. We used the admixture, curing compound only. No water was applied to the deck whatsoever. It was just the curing compound and the admixture, and it worked. There was minimal cracking observed. There was just over the piers in the negative moment regions, we did see some hairline cracks in the flow lines, but that's not uncommon. We saw favorable strengths and good pumping. I'll get into some of the other benefits here in a minute. But again, everything was positive. We tried it. Then Dan McCoy has broader reach due to his pumping side of the business, and other contractors heard about this, and there became interest. By the end of the year, we had actually poured a total of 27 deck pours on some 20 different structures using this methodology. You can see there, we had 5 different contractors involved who tried it, 6 different ready mix suppliers in 4 different districts. So it's a bit of a testimony there to how favorably this process was viewed, just because it caught on so quickly. This slide just shows a couple pictures of the pour with Beatty, I-65 over South Keystone. You can see that, again, white as a sheet of paper with the curing compound, 2 coats applied. We put burlap over the railing to avoid getting curing compound onto the railing steel. You can see the machine is here. We're not too far behind the finishing machine, getting things covered with that curing compound in a timely manner. The contractors are all required to use a motorized sprayer. One contract tried it in 19 with a hand pump sprayer, and you just can't put enough curing compound out with a hand pump sprayer. It's way too much work. And these motorized sprayers do a good job of really painting it white. So now I'm going to get into a little bit about what the admixture is. The term nanosilica has become a buzzword in the concrete industry. It's kind of used to refer to a lot of things, but it's a bit of a buzzword. Silica fume is a byproduct of the silicon manufacturing industry. It's something we have used for decades now. We use it in our silica fume overlays. It is basically a byproduct of the silicon manufacturing. It's pozzolanic. It is a fine powder, and it is 57 times finer than your Portland cement in the terms of surface area. There's a lot more surface area because due to the smaller particle size. When we talk about nanosilica, nanosilica is actually a man-made product from salts and metals in a tank. It is not a new material. Nanosilicas have been around for decades in other industries. They're just somewhat new to the concrete industry. They are also, it is just pure silica. Both of these things are just silica. The big takeaway is it's the size of the particle. These particles, where we were talking 57 times more surface area to a smaller particle size, now we're talking about a nanoscale. We're talking about a very small particle, and we're talking about 1,700 times more surface area than Portland cement or fly ash. So again, same chemistry, similar chemistry. It's just silica. It's just very small silica. Now it can exist as a fine powder. However, that doesn't work in concrete. You can't get it dispersed. So what we're talking about is colloidal nanosilica, and a colloid is just a suspension in a fluid. Milk is a colloid of fatty particles in a solution, where this is basically what we're talking about is silica, very small silica particles permanently suspended in solution. So a small disclaimer, this is not intended to be a video or a marketing campaign for this E5 internal curing admixture. I'm only wanting to explain to you what INDOT has done and tried with this particular product. The reason it's come to INDOT is because it has this product that was developed by an Indiana company named Specification Products, and they developed it, and it had been used, and it's been refined here in the Indianapolis area in the commercial world for the past few years. So again, based on everything I had previously said about my interest in curing compounds and learning about this, it was worth a try. So that's kind of why I'm the one talking about it, and why from a DOT perspective, perhaps we were closest to it, because it's kind of growing up here in Indiana. So it is a colloidal silica admixture, as I've mentioned before. It is a bit modified. This is a patented product. It is a unique product. I do want to mention the batching sequence is absolutely critical in order to making this work. It's something the ready mix industry understands, and how to use the products. They understand how to use all their products, but the batching sequence is critical in this particular product. The particle composition and size range are a couple of things that are also unique to this particular product. So internal curing, I say sort of, because when I first heard them using the term, to me, I was a little skeptical. Traditionally in the DOTs, what internal curing has meant nationally is using a lightweight fine aggregate, a saturated lightweight fine aggregate, to basically embed a reservoir of water that then gives up the water slowly over time to provide internal curing mechanism. So what this does is, due to the small size that I mentioned earlier of the particles, it has the effect of binding more water molecules to the grains of cement. So it has a similar effect, but that's a bit of a marketing term to use the term internal curing. But the more I've learned about it and seen it, I don't really have a problem with the term. It just is not done. What it's doing is not what we traditionally would have considered internal curing. This slide summarizes the benefits and things we had hoped we would see by using the E5 internal curing admixture. We did consistently see improved strength north of 600 psi flexural in 2 to 4 days. We saw good compressive strengths. Now, those were done simply by taking the samples and duct taping the molds shut and leaving them for 28 days to see what would happen, basically. And we were getting around 6,000 psi, which is the design strength of the mix in 28 days. I had seen in preliminary testing in the lab before we started all this that when I made a control mix and an E5 mix and we put them in the tank for 28 days, basically we didn't see any difference. It seems that in lab conditions, when everything has all the water it needs, there really isn't any difference. E5 seems to have its effect out in the real world where atmospheric conditions and water loss come into play. So it seems to shine out in the real world, but in the lab, it doesn't really show that much difference. We saw minimal to zero cracking on these decks. That to date, minimal has been reported, if any, on some of them. I went out and looked at one of the decks in December, and there was, again, no cracking, and that's certainly a positive for us. Reduced permeability / absorption is something I'll talk about here in a minute on another slide. That's been validated. Reduced calcium hydroxide is something that we have not really proven yet, but there is testing being done by others. Specification Products has initiated that, and those reports are coming here in the next 90 days or so, and I look forward to seeing the results of that. But I have seen preliminary data that seems to be favorable towards the reduction of calcium hydroxide. Improved workability is what drove a lot of this. The contractors liked it, their finishers liked it. Even though we said no water to be applied to the surface, I was a little bit surprised at how much buy-in we got with that. But it just, once they got their trowels, the finishers got their trowels on the mix, they just realized they didn't need additional water on the surface. There is a longer window of finishing perceived at the surface by the finishers. And we had a few contractors who had some screed breakdowns, and that after 20, 30 minutes of breakdown, when they started the screed back up, the mix is finished just like they had almost just been placed. That should not be confused with assuming there's a longer overall set time for the mix. You still have to maintain your usual pour rates because the mixes don't necessarily take a lot longer to set. You just have that longer finishing window at the surface. Minimal bleed rate, again, translates into lower permeability. These mixes just don't exhibit much bleed water at the surface. We did see that in October and some of the cooler temperatures and foggy days, it certainly took a little longer for that surface water to dissipate, which means you got to wait a little longer to get the curing compound on. But in general, these mixes exhibit very little bleed. This is also an opportunity for INDOT and a positive here to eliminate the evaporation retardant products. They are 90% water. They are more often than not abused and used incorrectly. If you apply them and forget them and don't touch them, they work. But as soon as you rub on them, they're rubbed into the surface, you're basically rubbing water in. And that's how these are typically used. Finishers grab them thinking they're doing something better and use them in lieu of water, but all they're really doing is rubbing water on the surface. So we are using this as an opportunity to really get these out of our culture, and they really are not needed with these mixes. Improvements in pumping are another thing that really drove this. Again, Dan McCoy, who pumped a lot of these mixes. R.L. McCoy has a lot of reach in that they pump for a lot of other contractors. He saw the lower pump pressures early on and how well the mixes flowed through the pump. That seemed to translate into very consistent air throughout all these pours. We just were not fighting the air. It usually came out between 6 and 7, and it just stayed there the whole pour with very little effort. The surprising thing, and I'll get to it a little later, is that didn't necessarily translate into the hardened air, and that was one of the more surprising findings of this whole thing. So a little more on that in a few minutes. The curing stays in place for months. I looked at one of the decks in 19 that we did, and it put the curing compound on in August. I looked at the deck again in December, and there was clearly still remnants of the curing compound in place. And faster opening to traffic is something that we have not done to date, but we are looking at. So we know we saw positive benefits during placement with the plastic concrete, but we still needed to validate what we were getting in the hardened concrete. I took 10 cores, 2 cores each from 5 different pores. 3 of those cores Purdue looked at under the scanning electron microscope. Now, these are fairly young cores. They were 24 days, 30 days, and 48 days at the time of coring. So again, very young concrete we're looking at here. But overall, the summary was that the concrete quality is good. However, most of the cores had, or all the cores had some micro cracking, which was attributed to autogenous shrinkage, which basically means that there's some moisture deprivation and the samples appear to be running out of water. So we saw varying degrees of the autogenous shrinkage cracks you can see in the image on the right. And then there was also large cement grains, varying sizes, I guess, that were not well hydrated. Now, these would expect to continue to hydrate over time, but at the age and the time they looked at them, there's quite a bit of unhydrated cementitious material. Now, a surprise was that the air void system in the hardened concrete ranged from good to poor. One cylinder had, or one core had good air. One of them it was kind of in the middle, and the other one had poor air entrainment. That was really surprising based on the observations and the testing we did of the plastic concrete. The analysis was that we believe that the autogenous shrinkage and the stresses developed may have destroyed some of the air bubbles, the smaller air bubbles, and in general, the lack of moisture or competing interests, I guess, so to speak, for water in the mix, perhaps did not allow the air void system to develop as well as would have expected in a couple of the cores. So that was a bit of a surprise. And as I mentioned, again, there's a significant amount of unhydrated cementitious material. So the takeaway from this was that, again, we got good concrete. We just feel like we need a little more water in the mix. Purdue also did absorption testing per C1585. Now that test typically requires a 4-inch core. The 6 cores that they analyzed from us were only 2 inches in diameter. So Professor Olick used some older cores to develop a method where he used some 4-inch cores and 2-inch cores to see how things would compare to our 2-inch cores. And what you see on the right are the reference specimens that were older cores. Again, our cores were fairly young, and they are the ones on the left. So what you see is that a number below 2 on that I value is a good number. You see that our numbers were below 2 on 5 of the cores. There was a 6th core that was removed. The data was a bit of a flyer, so he took that out of the data. And then you can see that our values were all well under 2 and compared favorably to the much older specimens of both 4-inch diameter and 2-inch diameter. Again, this is all very favorable. And in light of the fact that the air void system on a couple of the cores was not ideal, when you look at this absorption data, it's very favorable. So taking everything into account, again, the conclusion is that we got good concrete out of this methodology. These images show something that we observed with the curing compound. They did a good job of applying it. We want it white as a sheet of paper, but the next day on one of the jobs, we observed this crazing or cracking that was initially believed to be in the deck. We investigated and realized that it was really the cracking in the curing compound itself, and there were no cracks in the deck. This can happen if the curing compound is applied too soon and there's moisture under the curing compound. And so you need to wait for the sheen to dissipate and any bleed water to dissipate before curing compound is applied. You get into cooler temperatures and it takes a little longer for that to dissipate. So you need to be aware of applying the curing compound at the right time. The picture in the upper right shows something else we saw. These float marks from a distance with the shadows can appear to be cracking, but when you get up close, you realize it's just a float mark and some shadowing that really we thought they were cracks, but in the end they were not cracks at all. It was just shadows. So based on the findings, field observations from 2020, as well as the core data, INDOT is planning to move forward at this time with the process. At the time of recording this presentation, it is a draft memo that may or may not already be issued by the time the presentation is given. But at this time, it is a draft, so anything can be subject to change of what I'm about to show you. Anyway, the key points to the memo in the next 4 slides are that this is a unique process. It is tied entirely to the E5 admixture. We're not considering other similar admixtures. It is strictly tied to this E5 admixture. It is going to be for bridge decks, slab bridges, or reinforced bridge approaches. We are not adding E5 to other structural elements or other elements at this time. It's strictly for the bridge decks and the slab bridges and the RCBAs. That's so bullets for 1 and 2, self-explanatory. Bullet 3 is something we have not done to date. It is in response to what we found in the cores and the autogenous shrinkage. We are bumping up the water cement ratio maximum, or the target range is going to be 470 to 500 for these mixes. And then bullet 4 is to ensure that the front part of the load, when the water is induced into the truck initially, that we fully wet the front part of the load before inducing the admixture into the back of the load. And we think those 2 things will help the autogenous shrinkage as well as improve the air void system. The next section of the memo addresses items that are done during placement. These are 4 things that were done during all 27 of the pours in 2020. We require that a representative from specifications products be on site. I think this has been a significant part of our success so far. They have been physically present at the job site and at the plant to assist, and that has been very helpful. The water shall not be applied to the plastic concrete surface for any reason. We're putting it in writing, and to date, I was surprised at how well this was received. But again, once the contractors saw how well the mix was behaving, this really became a non-issue. But in writing, we say that we're not going to apply water to the surface for any reason. And I'm also saying that products marked as evaporation retardants or evaporation reducers shall not be used. As I mentioned earlier, we're pushing to get these out of our culture. They're more often than not, they're used incorrectly. So we are clearly stating we don't want them here. And the items, the finishing aids, these finishing aids can be used. To date, I think 26 or 27 pours did use the E5 Miracle Aid. Again, it's very little of it ends up being needed, but it does slick up the surface. And these other 2 products are similar technology that could also be used. I know the M2 Solutions product is available. It tends to be marketed more to the south, but any of these 3 products could be used if desired. So this section of the memo addresses items after placement. Specifically, the application of the curing compound. We require the motorized sprayer, as I mentioned earlier, 2 coats applied white as a sheet of paper. Bullet B here is written to give some flexibility about the timing. Obviously, we want to get it on there ASAP. However, in the cooler temperatures, it can take a little longer for the sheen to dissipate. So you don't want to trap that any bleed water under the curing compound. So again, we don't want to put the 2 coats on at the same time or just back to back. There needs to be a little bit of time for to let the first application set as well. So there should be enough freedom in that bullet B to allow you to work with the conditions that exist. Bullet C, again, we had one job where the the downward pressure of the sprayer almost kind of pressure wash the surface a little bit. So you don't want a lot of downward pressure. The curing compound needs to gently settle onto the surface. Protect exposed reinforcing bars. Bullet 2 addresses how to handle the acceptance beams. There's not a perfect way to handle this because we did on some jobs, we sprayed the beams with curing compound. We did get strength on them, but I feel like the most fair way to treat the beams is to go ahead and wrap them in wet burlap and plastic. Obviously, in sunny days or warm season, we need to make sure those are placed in the shade. We don't want to cook them. So we'll put them in the shade. You get into October, November, cooler months, we may go ahead and put those beams in the sun. But that's how we're going to handle the beams. Bullets 3 and 4, obviously we do not have anything on the deck now. So once we have strength, we are going to allow the deck to be opened at 5 days and 600 psi. This is a change. This is not something we have done to date, but based on the strengths we saw, we feel comfortable moving this direction. Bullet 5, for the purposes of determining cold weather concrete conditions in accordance with section 702.11, the curing period is still considered to be 168 hours. That's the trigger in the cold weather when you have to tent and have an enclosure if you're going to get into a certain temperature range within 168 hours. So that's why that is there. Prior to placement of the pavement markings, the deck does need to be cleaned at the location of the pavement markings. We do not want to blast off all of the curing compound all over the whole deck, just where the markings will be placed in order to ensure that they will adhere to the deck. And then lastly, on this page, I want to be in the loop to know where this is being done, and I'm requesting that the project people can communicate with me to make us aware where this is in fact being done. The last section of the memo addresses how to go about making a request. To do this process, the contractor needs to make the request through the project personnel at least 7 days prior to placement. The request will be reviewed by the area engineer, and then upon approval, a zero cost change order will be processed that will incorporate basically the requirements of the memo as previously stated, and then it will add this tag of E5 internal cure to one or both of these items in the contract. And the E5 internal cure creates an internal process for us to search and also be able to determine where this methodology was used.